Hello. This is the continuation of the lesson on merge sort. We are going to look at a couple of improvements to the merge sort algorithm in this lesson. Now, the first improvement that we consider is why should we divide the array all the way down to one element? It seems like a lot of wasted effort, especially a lot of wasted recursive calls to the merge sort algorithm. Why not stop at somewhere before that, right? So for example, the improvement suggested in your textbook by Horowitz and Sani is to apply a different sorting algorithm when n is less than or equal to 16. So given a large array, we start dividing it, but once we have arrays that are of size 16 or less, we no longer divide them. We no longer apply merge sort. Instead, we apply another sorting algorithm. The one suggested in the book is insertion sort. It is supposed to be good for sorting small sized arrays. We are going to study insertion sort later in the course when we look at decrease and conquer algorithms. So essentially, insertion sort is an n-squared algorithm, but it is supposed to be good for sorting small sizes. So why not stop merge sort, stop dividing, and call insertion sort whenever we have the size of the array being less than or equal to 16. So this reduces the number of recursive calls, and it is supposed to, in practice, give us better performance in merge sort. The second improvement that we look at is more involved. We need to understand it clearly. The question that the second improvement raises is, why do we copy so much data in merge sort? As we saw, 2 times n log n is the number of data element copies that are done in the merge sort algorithm that we have learned till now. Can we avoid that in some way, right? For example, can we avoid that and also avoid having the extra space? Remember the second array B, which was needed just to copy the elements. Can we eliminate that as well? This is particularly relevant when the data element is of a large size. Suppose we are sorting a set of strings and each string is very long, then copying those strings and the space required for copying those strings can be a big overhead on the merge sort algorithm. So we will see if we can avoid copying the data as well as that additional space required by having links to the data elements. So we only exchange links, we only swap links, we move links, we don't actually touch the data elements. The data elements are compared, but other than that they are not copied or swapped or moved around. That's the improvement that we are going to consider now. Of course, we do still need the extra space for storing links, but that is typically much smaller than the space required for keeping another copy of the data elements, right? So we copy links instead of the data itself. So we are given an array of 10 elements to be sorted. We do not actually move the data elements or copy the data elements. Instead, we sort them by using another array of links to those data elements. The starting point of a linked list will be in the 0th element of this linked list, and by traversing this linked list we will obtain the data elements in the sorted order. So how do we construct this linked list? We will see a bit later. If we had such a linked list, how do we traverse it to obtain or extract the data elements in sorted order? We will see that first. So for that, I can write a simple piece of code or algorithm as follows. Let's say k is the pointer or index I will use to traverse the linked list. First, I will set k to link of 0, the first element of the linked list, right? Then in a loop, we can say while k not equal to 0, do, for example, I can print all the data elements in sorted order by saying print a of k. And how do I go to the next element? I say k goes to link k, right? So that's the line which helps me go from one element to the next. K goes to link k. Let's see how this works.
by going through an example. So once again, we start at the 0th element of the linked list, and while the index doesn't become 0, we access the corresponding element a of k, and then to go to the next element we say k equals link k. So here is the final linked list that would result from sorting the given elements. If I were to expand or extract the sorted order from this linked list, we will start with 6. That's in the position 0 of the linked list, and then k equals link k would take me to the 6th element of the linked list, which is 8. The 8th element would take me to 9, the 9th element to 10, 10th element to 5, the 5th element says go to 2, the 2nd element says go to 3, the 3rd element says go to 7, and the 7th element says go to 4, and the 4th element says go to 1, and the 1st element says stop because it is 0, right? So if you look at the corresponding data elements for this array, a of 6 is 2, a of 8 is 5, a of 9 is 8, a of 10 is 8, a of 5 is 9, a of 2 is 22, then we have 56, then a of 7 would be 76, a of 4 is 108, and then a of 1 is 140. So that is the sorted order. So these are the data elements. This is the linked list in the links array. The only question is, how do we construct such a linked list? For that, we have a modified version of the merge algorithm, which takes an array as well as a link array and 2 starting points for sorted linked lists. So Q and R are the first elements, point to the first elements of 2 sorted linked lists, which have to be merged to produce a single sorted linked list. How do we do that? The resulting linked list, right, will be pointed to by this index k. What we do is we traverse both the lists until I naught, that is while I naught equal to 0 and j naught equal to 0, meaning both lists are not exhausted. That means both the lists still have elements. Then we compare the corresponding elements ai and aj. Whichever one is smaller, ai less than or equal to aj, that is the one that we will add to the resulting list k. In this case we add I, in this case we add j, right? So whichever is the smaller element, we add that to the resulting linked list, and if I equals 0, that means the first list is over, we simply append the second list to k. In the other case where the second list is over, we append the first list to the result. And then in the end we return the starting pointer of the resulting link. So this is very similar to the merge algorithm that we saw in the regular merge sort. The only difference is instead of copying and moving data elements, it uses linked lists. We'll go through an example to see how this actually works, how the indices to the links are manipulated to construct a single merged sorted list of data elements.
To write down here the values for the variables q, r, I, j and k, right? Let me change the color. Right? So first I want to merge this with this. That means I have a sorted linked list of one element which contains the data 140 and another which contains 22. I want to merge those two. So the value of q will be 1, r will be 2. I will just send those as the input parameters to the merge one algorithm, right? So immediately it says I is the same as q, j is the same as r, and k is 0. So we start by copying q and r into I and j and writing 0 in the for k. While I not equal to 0 and j not equal to 0, that means we have not hit the end of any list. Both are not 0. I is 1 and j is 2. Compare ai and aj. So if I compare these two, in this case ai, which is 140, is not less than or equal to aj, which is 22. So we go to the else part of the algorithm, and then it says link k is j. That means link 0 should become j. Link 0 should become j. So I will write 2 there. And then it says k should become j. So the new value of k is 2. And then j should become link j. So the value of j should become link of j. So link 2 here. By the way, all of these blank values are assumed to be zeros. So j becomes 0. Right? And then if I is 0, I is not 0, then we say link k is I. The new value of k is 2, link k is I. Right? I is 1. So we write 1 there, and then you return this value. Right? So what does this mean? Right? How is it that it has sorted these two numbers? Right? Let's write that down. So what has happened here is we start with 2. That means the second element of the array, 22. And the next element is to be found here in the second element of the link, 2, and that is 1. So that means the next element is 140. So it has sorted them by placing 22 before 140 in the linked list. Right? So this is what is returned. So that's how merging works. Now let us run it one more time for these two elements. Right? So now q will be 3, r will be 4. So immediately I becomes 3 and j becomes 4 and k is 0. Now it says while I not equal to 0 and j not equal to 0 do, is ai less than or equal to aj? In this case it is. Right? 56 is less than 108. So it says link k should become I. Right? That means link k, link 0, his new value will be 3. Right? This value is old now. New value will be 3 and k becomes I. So the new value for k is also 3, and then I is link I. So the new value for I will be whatever is there in the third position, which is 0. Right? There is a 0 here in this. So implicitly there is a 0 there. Now we say if I equals 0, which is true, right? Then link k should become j. That means link 3 should become j, which is 4. Right? And we return link 0. So in this case this is returned, which means you start with the third element and then that takes you to the fourth element. Right? 3 to 4, 56 and then 108. So we have these two lists residing in the link array because this element was untouched. So it is as though the link array now has these entries. Link 0 is 3, link 1 is 0, link 2 is 1, link 3 is 4, and the rest are all zeros. Now I want to merge these two arrays. That means 1 and 2 to be merged with 3 and 4. How do we do that? We give the starting pointers. The starting point for this was 2. Right? So 2 and 3 will be the values for q and r. Why? Because if I start from 2, it says 140, and then the so this 3 was the starting position for the second array and 2 was the starting position for the first array. Sorry. Right? So if I give those two, then what happens? I and j become 2 and 3, k becomes 0. Now it says while I not equal to 0 and j not equal to 0 do, if ai is less than or equal to aj. So now we are comparing 22 with 56. 22 happens to be smaller than 56. So in a sense we are given this is one linked list to be merged with the other linked list, right? One says 22, 56, 22 and 140. And the other one says 56 and 108. We need to merge those two. Right? So we compare 22 and 56. It is actually 22 is actually less, right? So then it says link K should become I. Link 0 should become 2. That will be the new value. K should become I. So K becomes 2. And then I should become link I. I should become link of I. Link of 2 is 1. Right? So I becomes 1 now. And then if is I 0? No, I is not 0. So we go back to the loop and then we compare AI and AJ again. But I and J are now 1 and 3. Right? So we compare 140 with 56. 140 is not less than 56. Right? So now we go to the else clause which says link K is J. That means link 2 should become 3. That's the new value for that. K should become J. So K becomes 3. And then J becomes link J. J becomes link J, which was 4. Right? Now, so J becomes link J, 4. So now we go back and compare 1 and 4. That means I'm comparing 140 and 108 now. Right? Again it is not less. So link K becomes J. Link of 3 becomes J. The value for J is 4. It is already true. K becomes J. So K becomes 4. And then J becomes link J. So link of 4 becomes 4. J becomes link of 4. So J becomes 0. So in this case we exit because J is now 0. Now you ask, is I 0? No, I is not 0. So therefore we do link K is I. That means link of 4 will become I. Right? So this rest of the remaining elements will remain zeros. And it returns this. Phew, let's see if this works. Let's see if we have got the correct answer. Let me use some other color. Right? So we start with this position 2. That means we start with 22 because this 2 is pointing to this 22 here. Then I jump to the second position of the array which is pointing to 356. That is now pointing to 4 which is pointing to 108. That is now pointing to 1 which is now 140. And that is pointing to 0. That means we end there. So we did get a sorted linked list. Right? So this is how it works. We can merge first 2 elements, then 2 other elements, and then we merge those 2 sorted linked lists to obtain a sorted linked list of 4 elements. You really need to work out this entire example or another example by going through the while loop and the if statement in the merge one algorithm. Only then you will actually see how this whole thing is working. Right? I've just shown a small example up to size 4. Right? So let me. There is a third possible improvement to this merge sort algorithm, which is to eliminate recursion itself. As you can see, what really happens is we start with a large array. Right? We start with a long array. We break it up into 2 small parts. Right? Then you break it up into 2 smaller parts. Right? And so on. And each of them results in a recursive call. Then you have to unwind the recursion when we do the merge and get back the original result. So this is a top-down approach which is resulting in all those recursive calls. Why not write a bottom-up version of the algorithm? In that new version of merge sort algorithms, you just take consecutive array elements and start merging them and then start putting them together into larger and larger pieces. So if you invert the entire structure of the algorithm and work bottom up, then you can avoid recursive calls which will save you stack space during the execution of this merge sort algorithm. We will not actually look at such an algorithm. That's an exercise for you to go and write a non-recursive version of merge sort which works bottom up from smaller arrays to construct larger sorted arrays. And you can combine both of these techniques. You can do that with links to once again avoid copying data elements. So that's what we learn about merge sort. Thank you.